This book doesn't go into a lot of details of the energy balance. It's there, but it's not explained in the way a basic text would. So I grabbed this material from the other course I have on my channel called Ocean Atmosphere Dynamics, using the book by John Marshall and Alan Plum. So these are figures from that chapter. Let's just run through it just so that you are comfortable with it. So here is the sun emitting energy in all the electromagnetic spectrum, going from gamma rays, X-rays to various infrared wavelengths, visible where Earth receives most of its energy, and then you have I should have said ultraviolet, and then visible, and then long wave, microwave, radio wave, and so on. And here is Earth sitting at 255 Kelvin global mean temperature, and we have to do the energy balance basically to explain how the flux that's coming at the top of the atmosphere, basically rays are parallel because we are far enough away from the sun, and the flux is Q divided by 4 pi r squared. That's how the sun's energy is going to be emitted from its surface, from each point on the surface. And the properties we need are, again, as we mentioned in the previous podcast, Venus, Earth, Mars, and Jupiter. You can look at their size, the energy they receive, their average albedo. Earth is here at 0.3. Venus has a very high albedo and yet a very high surface temperature, whereas Mars has low albedo, low amount of energy being received, and very cold temperatures. And here is Earth with its Goldilocks syndrome, as we said. This is the wavelength at which the energy is emitted by the sun, and this is the Planck curve which relates the energy to the wavelength. So the maximum temperature of 6,000 Kelvin determines the where the energy is maximum that we receive. And here is the energy emitted at different wavelengths for black bodies at several temperatures. So here is the wavelength energy emitted based on the mean temperature. So black body is something that, a perfect black body is something that absorbs all the energy it is receiving, achieves an equilibrium temperature, and its energy is going to be determined by, its emission of energy is going to be determined by Stefan-Boltzmann law of sigma t to the fourth, where sigma is the Stefan-Boltzmann constant. Earth is not a perfect black body, so we will see that it has an emissivity which is less than 1. 1 is a perfect black body, and we have to see where Earth emits in terms of its wavelengths and temperature. The other thing that matters for Earth's energy balance, of course, is albedo, the reflectivity. So how much of the incoming solar energy is directly lost back to space. It depends on the surfaces, so ocean, forest, cities, grass, soil, clouds, snow, and old snow and fresh snow, and so on. Obviously, bright white surfaces like snow and ice have high albedos. Whether it's old or dirty and whether it's fresh and clean will determine how bright they are. Clouds range from as low as 30% albedo to 60 to 70%, and we will see that Earth as a whole, averaged for the globe, has albedo of about 30% or 0.3 in the calculations we will do. So the energy balance basically is done by looking at the global mean first, how much energy is intercepted by the Earth in terms of the energy that it will collect from the sun as a panel. So since Earth is a sphere and the rays are coming in parallel, it depends on the area that the Earth projects to the incoming parallel rays of the sun, which is a circle. So imagine a basketball, a flashlight, and the shadow will be a circle just like it's shown here. So if Earth's radius is a, then area is pi a squared, obviously, and the surface albedo distribution looks like this, with bright surfaces of the Greenland glacier, Antarctic glaciers. Deserts tend to be very bright, mountain glaciers here, snow on the land, and so on. Okay, and the solar power incident on Earth then is S0, which is the flux at the top of the atmosphere per unit area, times pi a squared is the disk that's collecting the solar radiation, which amounts to this much solar radiation absorbed by the Earth, then what is lost because of the albedo and what is received. So 1 minus alpha times S0 pi a squared. So 30% of this is lost. This is what remains to heat the Earth, evaporate, and create all the circulation. Emitted radiation per unit area is sigma times Te to the fourth, where Te is some effective emission temperature. We don't know exactly where it's coming from in terms of the atmosphere. Sometimes it's going right from the surface to space, like on a desert where there is no clouds. So there is dust and aerosol which may affect things, but essentially they are losing straight to space. Clouds are emitting from the top, and so on and so forth. So there is some effective emission temperature, and each point on the Earth is emitting long wave radiation. So the total is going to be area of the sphere 4 pi a squared times sigma Te to the fourth. If you solve that equation for the emission temperature, you end up putting the values for sigma, which is known as 0, which is 342 watts per meter squared or so, and alpha, which is 0.3. You end up with an emission temperature of 255 Kelvin, which is minus 18 degrees centigrade, which is obviously too cold because the emission temperature, Earth's average temperature, is 15 degrees centigrade. So we need 33 degrees of warming on this calculation, which obviously has to come from greenhouse effect. So you look at the sun's radiation being emitted at 6,000 Kelvin at the outer surface, and Earth's emission at 255, the 255 Kelvin that we just derived here. You can see you need to add absorptivity at the ground level and at the upper atmosphere by the various gases that are present in the atmosphere, and they have all these absorption bands, okay, which is what gives us the greenhouse effect, right? So if you look at the top of the atmosphere, things like methane, carbon monoxide, carbon dioxide, etc., and water, ozone, etc., have various bands, wavelengths at which they absorb the outgoing long wave energy. That's what we are interested in. Those that allow the short wave to come in, we already know it amounts to about 30% loss, and the rest is going to get into the surface, and some will be absorbed in the atmosphere, and so on. So this is what we are trying to do. So looking at Wien's displacement law, which relates the energy to the maximum wavelength and the average temperature at which it emits, that curve that we saw. So the maximum wavelength of Earth's emission then is related to, we can do it relative to the sun, because we know sun is emitting at 0.6 micrometers, so 6,000 is its maximum temperature, and Earth's temperature at 255. Then you have wavelength of 14 micrometers. Okay, I'm just running through those because this is simple stuff, and you can also see my other podcasts from the Ocean Atmosphere Dynamics course. So when you want to do the energy balance, you go away from the global mean that we did, and you zoom down to a unit area, where you are now going to look at the sun's energy distributed on the surface, so 4 pi a squared, which means on a unit area it's going to be solar constant S0 divided by 4, because you are distributing over 4 pi a squared, and out of that albedo is going to reflect some of it, and we put in, for simplicity, one atmospheric layer, which, instead of losing the outgoing long wave from the surface, which is generated by the heating from the short wave, just listen carefully and look at it. It's very simple linear calculation. So surface temperature is going to reach some Ts. That's going to determine the outgoing long wave from the surface. And the atmosphere is opaque to the outgoing long wave, so it's going to absorb it and reach a temperature of Ta, which is the atmospheric temperature. And atmosphere is going to emit to space and also back to the surface. So the long wave energy of A is going to come out of the atmosphere as sigma Ta to the fourth, going out to space and back to the surface. So now the surface is receiving short wave, because we have assumed here that the atmosphere is completely transparent to the short wave, and all that 1 minus alpha is going to reach the surface. And it's also receiving long wave from the atmosphere, infrared energy from the atmosphere. This is the key effect of greenhouse gas. Greenhouse effect makes the surface warmer because it's putting this additional infrared energy back to the surface. So you do the calculations, you look at average solar energy flux received divided by the area over which you are distributing it, which gave us S0 over 4. Because instead of averaging over the whole sphere, we are looking at unit area for the energy balance. Make sure you understand that part. It's very simple, and yet you should be careful where these factors come from. So the outgoing long wave from the atmosphere in both directions is sigma Ta to the fourth, and you equate sigma Ta to the fourth to the energy that is being received. So if you look at the top of the atmosphere, this is the short wave energy received, this is the outgoing long wave energy, and so Ta here in this simple case is the effective emission temperature. But you know that A is also coming down to the surface, so the surface energy balance is going to be sigma Ts to the fourth going out and the solar that is coming in. So the surface has to balance the outgoing long wave with the downwelling long wave from the atmosphere, which is this part, and the short wave that's coming in. Very simple linear calculation. You plug that into the previous equation, you end up with sigma Ts to the fourth. This is of course sigma T to the fourth itself, so you end up with 2 sigma Te to the fourth. So Ts, the surface temperature, is going to be 2 to the power of 1/4 times the emission temperature. Hence, a greenhouse layer is going to increase the surface temperature, which means we're going to go from 255 to something much warmer, because this 303, which is much larger than the average of 15 degrees centigrade. Why? Because we made a simple assumption that atmosphere is just one layer, it's completely transparent to short wave, and it's completely absorbing the outgoing long wave from the surface, and so on. Obviously the atmosphere has got multiple layers, and it's got an emissivity, which means it's not a complex perfect black body, and it's got many layers and so on. Okay, so that adds a little bit of complication here in terms of emissivity or absorptivity. Okay, a black body which is not perfectly black is not going to absorb all of the energy and emit back. It's going to absorb only part of the energy, which means it's going to emit only part of the energy. So if epsilon is 1, it's a perfect black body, and we get our earlier relation. If it's less than 1, then we are going to increase the effect here, because this is going to be divided by decrease the Ts. Okay, so if this is less than 1, this is going to be reduced because you are going to divide by 1 point something. Let's say its emissivity is 0.7, then it's going to be 2 divided by 1.3, so the surface temperature is going to be less warm than if it's a perfect black body, in which case this would be 1, and it would be 2 to the 1/4 Te. Okay, so that's the simple calculation, and this is just repeating some of the points. And I'm not going to go too much into it, and essentially you will need more complicated calculations to get to the value of 15 degrees centigrade as the average temperature of the Earth. So I'll come to how Peter does these calculations in the next podcast, but this energy balance podcast is a little long, but it's worth listening to. I'll repeat some of the points with the way Peter does it in the book.